we are going to discuss Faraday's law of electromagnetic induction. Let us take a simple coil. Let us connect one battery across it. Hence, there is a magnetic field surround it. Let us take another coil connected across a galvanometer as shown here in the figure. Now, we will hold the second coil nearer to the first coil. More specifically to say, hold the second coil under influence of magnetic field of first coil. Now, we can observe that there is no voltage appeared across the second coil. There will be no deflection in the pointer of the galvanometer. Although at that condition, there is magnetic flux linkage in the second coil from first coil, but no voltage induced in the second coil. Now, we move the second coil inside the influence of magnetic field of first coil. Now, we can observe that during movement of the second coil, the pointer of the galvanometer deflects. This indicates that some voltage has been induced across the second coil while the second coil was moving. Now, let us move the first coil keeping the second coil stationary at its place. In that case also, we will observe that there is a voltage induced across the second coil. In this case also, the pointer of the galvanometer deflects. In first case, there was a flux linkage in the second coil from first coil, but no voltage induced in the second coil. In the second and third cases, there was still flux linkage in the second coil from first coil, but the flux linkage was changing due to movement of coils. So we can now conclude, whenever a coil or any other conductor comes under influence of changing magnetic flux, there is a voltage induced in it. The voltage induced due movement of the conductor or magnetic field is called dynamically induced voltage. We can create the same condition without any movement of either of the coils. In that case, we have to apply an alternating voltage across the first coil. This produces a changing flux. This changing flux will link the second coil, and for some reason there will be an induced voltage across the second coil. In that case, both conductor and magnetic field are physically stationary. The induced voltage in this case is called statically induced voltage. In all events, when there is a changing flux linkage, a voltage is induced. This phenomena was first observed by Michael Faraday, and he stated as a law called Faraday's first law of electromagnetic induction. Faraday's first law says, when a conductor links with a changing magnetic flux, there is a voltage induced in it. Now, we will move the second coil faster inside the influence of magnetic field of first coil. We will see that during faster movement of the second coil, there is more deflection of pointer of the galvanometer connected to it. Same thing happens if instead of second coil, we move the first coil faster. So, when relative motion between magnetic field and conductor increases, the induced voltage across the conductor is also increased. The increase of relative motion between magnetic field and conductor means increase in rate of change of flux linkage with respect to time. Michael Faraday stated that in his second law of electromagnetic induction. His second law states, the magnitude of induced EMF in a conductor is directly proportional to the rate of change of flux linkage with respect to time. If we observe the pointer movement of galvanometer during movement of the second coil or first coil, we will find that the movement of the pointer in one direction when both coils come closer and the movement of the pointer in opposite direction when both coils go away from each other. When the coils come closer, there is an increasing rate of flux linkage, and when the coils go away from each other, there is a decreasing rate of flux linkage. Thus, the polarity of the induced EMF in a conductor depends upon whether the rate of change of flux linkage is increasing or decreasing. Now, let us come to the mathematical form of Faraday's law of electromagnetic induction. If there is n turns in second coil and rate of change of flux linkage with respect to time in second coil is d phi dt, then the induced EMF in the second coil is E equals to minus n d phi dt. Here, two things to remember. 1. Constant of proportionality is 1. This means EMF induced in a turn of coil is exactly equals to the rate of change of flux linkage with respect to time with it. 2. There should be a minus sign in the left hand side of the equation. This is to justify the Lenz law, which states that polarity of the induced EMF opposes its cause, which is changing flux linkage. Hope you got a basic idea of Faraday's law of electromagnetic induction. Thank you.